All right, welcome to the first lecture in Unit 7. It says chemicals walk the line. The quote we have is "Y'all can't walk no line" by June Carter. This is basically our first lecture over chemical equations and balancing chemical equations. So what we're hopefully trying to learn, our learning goals for this, is students will use chemical symbols to express chemical reactions. So we'll look at all the fine details of those chemical symbols and what they actually mean. Secondly, we'll convert between written descriptions of chemical reactions and their chemical symbols, and then from their chemical symbols back to a written description of what they are. And then lastly, we're going to apply the law of conservation of mass to chemical reactions, which that basically just means we are balancing. So let's jump right into it. What we already know. Evidence for chemical changes can include change in state. So we could see something go from a solid to liquid. That's a change in state. Not always means that there's a chemical reaction, but sometimes it can. Like with the combustion of hydrogen, we see that it go to gases go into a liquid. We can see change in temperature, meaning that it produces heat from that chemical reaction, or it gets colder from that chemical reaction. And then we have the change in color, which you can see here. Two liquids are being put together, and we see a nice change in color. And we also know that we have sodium chloride and the symbol for sodium chloride in NaCl. One of the main things about balancing chemical equations, using chemical equations, is we have to be able to write the formula from the name and know what the name is from the formula. We got to be able to do that coming into this. It's probably the most important step out of all of it, because if we mess up there, everything else is pretty much messed up. So what we learned in the lab is that the law of conservation of mass applies to chemical reactions. That when we look at the law of conservation of mass, that it has to equal out. And so by adding mass to one side, it'll produce more mass on the other side. So if we put more mass here, that means that there's going to have to be more mass here. And so everything has to balance out, and that's where we get those chemicals walking that fine line. They have to balance. So in a chemical equation, the reason why we have them is that they reduce the number and types of variables. So it kind of limits our scope of things. Instead of having a big paragraph describing a chemical reaction, we can have something in a nice chemical reaction in the chemical equations all written out in one line. Really helps us organize information, so we're not searching for things. And it provides pretty much two things. It provides a quantitative information, which this quantitative information, talking about numbers, things that we're going to use in the next unit when we start looking at stoichiometry and things like that, and also qualitative information, so actually describing what's happening and looking at the descriptions of reactions. And so chemical equations give us a lot of information if we know how to read them. Now, the pieces of chemical reactions or the chemical equations. The first thing we have are reactants. Now, reactants are the starting pieces of the puzzle. They're the very beginning, and we see these as normally on the left side of the arrow. Not always, but the majority of the time you'll see them on the left side of the arrow. They are what is used up in a chemical reaction. Okay, it's what's no longer left over. It's what we start with. Now, products, on the other hand, products are the ending thing, the ending product. It's what comes from the reactants. They are non existent before the reaction takes place, and then after the reaction is complete, you have the product or what is created. Normally, in general, they're on the right side of the arrow. They can switch sides, and we'll see that in an equilibrium equation, which we'll look at, which is just a big word that means a chemical reaction that goes backwards and forwards. And then also pieces of the puzzle, we have catalysts or inhibitors, and these are written above the arrow, which we'll talk about that. In a chemical reaction, we have an arrow. If it's written above the arrow, then we see that we have a catalyst or inhibitor, but those are the kind of the pieces, the main things that go into a chemical equation. So when we're looking at the parts of a chemical reaction, we can see that what we just said. We have our reactants on the left side of the arrow. We have our products on our right, and then we have some catalysts in the middle. Now, when we're looking at this, what we see is that we have our arrow in the middle. And the one thing we like to say about products, the arrow always points towards the product. So I could reverse this and make the arrow go the opposite direction, and we would know that the arrow points towards the products. So we see that we have the products over here because that's what the arrow is pointing to, and then our reactants over here. That's normally how everything's going to be set up. Now, the chemical equation, the symbols that go into it, we need to know these because they tell us a lot of information. The arrow just means to yield or produce or to form. It's saying that a chemical reaction is taking place. Here, with the reversible reaction, so the double arrow going backwards and forwards, that's that equilibrium equation that I was talking about because it goes backwards and forwards and it kind of exists in an equilibrium state. Now, after a chemical formula, so say we have NaCl, sodium chloride, yay, table salt. When we're looking at this, if I have an S after NaCl, that just means that it's a solid. If I have an L, that just means that it's a liquid. If I have a G, it's a gas. And this one you might not know is AQ, which means aqueous or aqueous. That is, when we talk about that, that means dissolved in water. So if I have AQ after NaCl, guess what I have? It's salt water. And so it just means dissolved in water. So the wonderful arrow that we have right here, if we have that arrow and we have a triangle above it, that means that heat is added to it. That means that heat is necessary for the chemical reaction to kind of start. If we have our potassium iodide, if we have that above the arrow, that just means that potassium iodide is a catalyst. It helps speed up that reaction. And then the number, if it's in front of the chemical formula, so say I put a 2 in front of NaCl, that number is what we call a coefficient. Now, coefficients represent the number of moles of that substance. So if I put a 2 in front of NaClAQ, that means I have 2 moles of aqueous sodium chloride. And that is just our coefficient that goes in front. Chemical symbols, really important in chemical equations. The other thing we have to remember in chemical equations that if we forget can make our lives kind of horrible because it messes everything up, okay, especially in our chemical equation world. So that is Brinkelhoff. So Brinclhoff, Brinkelhoff. Brinkelhoff represents diatomic molecules. So when we're thinking of diatomic molecules, diatomic, di meaning 2, when bromine exists, it doesn't exist just as one single atom. So none of these atoms exist in nature as one single atom. So when bromine is by itself, we write bromine as Br2. When iodine is by itself, I2. When nitrogen is by itself, so nitrogen gas, N2. Now, the key thing here is when they are by themselves, when they're not in a chemical equation. So if I'm looking at a chemical equation, say I have sodium bonded to chlorine, that's just NaCl. But if chlorine is by itself, it's Cl2. And the key thing is by itself. Another thing you can think of, if Brinkelhoff, you don't like to remember it that way, you can think of as the 7 atoms starting at 7. Or start at 7 on the periodic table, make a 7, and then don't forget hydrogen. Okay? So you can think of start at 7, make a 7, so nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and then hydrogen. Okay, Brinkelhoff or that, just remember these guys because you need to know them, because you forget them, makes everything a little bit more difficult. Now, one thing we'll practice is going from translating from words that we see just in a paragraph like this into the actual equation. And so we can kind of look at this, and it says the student places hydrogen gas into a sealed chamber containing pure oxygen. A spark ignites a chemical reaction as seen in the combustion of the gas, resulting in liquid dihydrogen monoxide. And so when we're looking at this, we can kind of pull pieces out, and you can kind of see that we did that. We have hydrogen gas, pure oxygen, A spark ignites in a chemical reaction as seen in the combustion of the gas resulting in liquid dihydrogen monoxide. So we can see all that really means is just an arrow. And there's our pieces. Hydrogen gas, oxygen gas, liquid dihydrogen monoxide. And then what we do is we just take those words and write the symbols. Hydrogen, oxygen, dihydrogen monoxide. And we can see we have gas, gas, liquid. And then anytime you write an element, you got to check. Is it Brinkelhoff? Is it a diatomic? So hydrogen's by itself. So we write H2, O2, and we make sure of that. And then we have our equation. And we're going to get into balancing towards the later part of this. So yes, this is not balanced yet, but we'll get to that on how to do it. So let's practice one of these. It says solid sodium reacts with chlorine gas to form sodium chloride. So let's take these words and let's take it apart. So we have solid sodium reacts with chlorine gas to form, that's another way to say produce. Reacts really means just plus sign, to form sodium chloride. And we'll say that it's solid sodium chloride. So when we set this up, solid sodium, Na, and it's S. Now check, is sodium a part of Brinkelhoff? No. So don't worry about putting a 2 there. Plus chlorine gas, Cl. Is chlorine a part of the of Brinkelhoff? Yes, it is. So we put 2 there, and we put a G for gas to form sodium chloride. Now here's the trick where you got to be able to write the formula. Sodium chloride is a diatomic, so you have to crisscross. So Na plus 1 Cl, minus 1, not plus, minus 1, and then we just crisscross and bring down the numbers to get NaCl, which will say that it's a solid. And that would be our chemical equation. Looking at our next one, it says the scientist heats a piece of solid magnesium in a Bunsen burner. So heat's added. What does that mean? Triangle. And it says the light produced continues even when the flame is extinguished. So a chemical reaction's taking place. That's what that whole sentence means. Chemical reactions taking place. That's the arrow. And it says the metal disappears, leaving behind a white powder. So we have a white powder. Write an equation based on the description. So we got to think. Magnesium sitting there by itself, it's reacting. What could it be reacting with? Well, that magnesium is going to be reacting with, and it's solid, the oxygen in the air. So O2, because oxygen is a diatomic, and it's in the air, so it's a gas. And we see we put the arrow above, the triangle above the arrow, and it forms a white powder. Well, what's reacting is magnesium and oxygen, so we write magnesium oxide. So Mg, which is plus 2, oxygen, which is minus 2. Since the 2 and the 2, they can reduce down to a 1 and a 1, and then we crisscross these guys, and we get our MgO. And since it's a white powder, we'll say that it's a solid. And there's our chemical equation. Obviously not balanced. So last question, our mastery question. It says pure distilled water, yay, distilled water, H2O, and potassium hydroxide, that is the catalyst, are placed in a beaker with a positive and negative wire. The wire is connected to an electrical source. Gas forms on both ends of the wire. Write the possible equation for this reaction. So when we're looking at this pure distilled water, that is just good old H2O, but it's a liquid. Okay. It's placed in there with our potassium hydroxide, KOH, and it produces 2 gases. Guess what those gases would be? Hydrogen gas, and we put H2 because it's a diatomic, and oxygen gas, and we put O2 because it's a diatomic. And we see we have our chemical equation. Now that we've gone from words to the chemical equation, let's go from the chemical equations to words. Now the symbols become very important when you're translating from the equation to words. We have to pay very close attention to what they are. Remember that the numbers in front, and we're going to talk how those numbers in front get there in just a little bit, but those numbers in front represent the number of moles. So when I'm looking at this, we know that 2 moles of hydrogen gas reacts with 1 mole, because it's not a number there, it's understood to be 1 mole of oxygen gas. And it produces 2 moles of dihydrogen monoxide, or liquid water. So let's practice this. The number one thing we need to understand are the symbols. What do they mean? So let's define each one of these. Remember that just the regular arrow, it means that to yield or to produce, or it could be to form. The double arrow means that it exists in equilibrium, which just means it's a reversible reaction. We see that this is solid, then liquid, gas, and the last one's aqueous, which means dissolved in water. The triangle means heat is added. If we have a symbol above the arrow, we know that it's a catalyst. And then the numbers in front represent, those are coefficients, and they represent the number of moles. So, jumping into our next question. We're looking at this, it kind of gives us an outline of it. It says liquid dihydrogen monoxide, potassium hydroxide above the arrow, then we have hydrogen gas and oxygen gas. So an easy way for us is we should look at this and go, hey, that kind of looks kind of familiar. Yeah, it's the example that we did before. So we could say that pure distilled water and potassium hydroxide as the catalyst are placed in the beaker. We see the beaker there, with a positive and negative wire. We know it's positive and negative by looking at this. And then we say that it's connected to an electrical source. And then a gas forms on both ends of the wires, and it produces a positive and negative, which it produces 2 gases. We say it produces hydrogen gas and oxygen gas. Next one, very similar. We have solid magnesium plus oxygen gas produces magnesium oxide. So what we could say, the triangle above means heat's added. So we could say that heat is added to solid magnesium metal, which reacts with the oxygen in the atmosphere, and it produces a white powder of magnesium oxide. And so that's one way that we could say it there. Now, the law of conservation of mass. The law of conservation of mass says that matter cannot be created or destroyed, but can change from one form to another. Essentially, summing all of this up, whatever we start with is what we finish with. Okay, those atoms get rearranged and they can be put together in different ways, but what we start with is what we finish with. We have to have the same number of atoms beginning and ending. We can't just make up atoms from anywhere. All of your work will be invalid when working with an unbalanced equation. So later when we get into stoichiometry, when we don't use a balanced chemical equation, nothing works. And so have to have a balanced chemical equation. It's what everything stems from. It follows the law of conservation of mass. So when balancing chemical equations, the only thing that you can change is the coefficients. You cannot change anything else. You cannot change the subscript ever, ever, ever. You can never, ever, ever, ever change the subscript. So I can't just take H2O and just decide, hey, to balance the equation, let's make it H2O2. If I do that, by changing the subscript, I change what the molecule is. And so you can think, oh, no big deal, right? Well, H2O and H2O2, very different results when you put them in your hair. If you put H2O in your hair, you can clean it. It's water. Yay. Good job. Go swimming. Water in your hair, no big deal. H2O2, however, is hydrogen peroxide. If you put hydrogen peroxide in your hair, you have a much different effect. Okay, so you can't change the subscripts. The only thing you can change are the coefficients that go in front. So, the steps in balancing an equation, and this is in general. Sometimes you just got to look at it and go, okay, let's go backwards and fix something and everything else. But in general, if you need a place to start, this is a good place to start. Number one, start, and this is probably the most important thing out of all of them, start and write a correctly written chemical equation. Okay, if you don't start with a correctly written chemical equation, meaning all of the symbols written out, so we have our NaCl as sodium chloride. If we accidentally put it as NaCl2, big deal, it's not going to work out. So we have to start with a correctly written equation. Next, in general, we can normally balance the metals first, then balance the polyatomic ions, the nonmetals, hydrogen, and oxygens. And so some people say this is MeNO, so M, ion, nonmetal, H, O. Kind of a little thing you can use. It works majority of the time. In general, you just have to look and you have to balance everything out and make sure you're taking it piece by piece. So let's look at one, steps in action. So start with a correctly written equation. Yay, it's correctly written. Next, we balance the metals. Well, in this case, the only metal that's up here is copper. So copper needs to be balanced. We have one copper here. How do I know that I have one? Well, it has a subscript. It's not there. It's just one. So to balance this out, since I have one before and two after, all I do is just put a 2 in front of my copper, because 1 times 2 is 2. So now I have 2 coppers and I have 2 coppers. Next, we balance the polyatomic ions. The only polyatomic ion up here is sulfate, and I see that I have 1 sulfate. How do I know this? Because if I had 2 sulfates, I would have a parentheses and a 2. I don't have that. So that just means I have 1 sulfate. 1 sulfate, 1 sulfate. Hey, that works out well. Next, balance the fluorines. So when we're looking at the fluorines, and that's why I put a 1 here and a 1 here, you can see, balance the fluorines. Since this is a 1, we also multiply that by 2, which we already put there before. So 1 times 2 is 2. That means I have 2 fluorines. And over here, guess what? 2 fluorines. So before and after. Next one, balance the hydrogen. So when I look at it, I have 2 hydrogens right here. I have 2 hydrogens right there. Yay, balance. Good, keep going. Next one, it says balance the oxygen atoms. So if I look, and remember, some people get confused on that. That sulfate doesn't really count because it's not an oxygen. That's an ion. But when we're looking at it, we have 2 oxygens on the reactant side and 1 oxygen on the product side. So to balance that out, what we have to do is we go ahead and we put a 2 right here, which now that means I have 2 oxygens and I have 2 oxygens. But the one thing you got to pay attention to is by putting a 2 right here, how many hydrogens do I now have? Oops, that means that I have 4. So I'll have to put a 2 right here to balance that out. 2 times 2 is 4, but by changing that, what did I also change? The number of sulfates. And so that's why I had to put a 2 right here. So you really have to, whenever you put a coefficient, you have to look at all the things that it changes, making sure that you accommodate for them. So let's start with this and balance the chemical equation below. So the one thing you can do is kind of set up a little chart. So we have our iron, oxygen, and those are the only 2 elements that we have. And we have to balance it out. And just draw a line down the middle. Okay? And we look on the reactant side, how many irons do I have? I have 1. On the product side, how many do I have? 2. Well, that's not balanced. We'll have to fix that. And on my reactant side, I have 2 oxygens. On my product side, I have 3 oxygens. So I need to balance all of this out. So we can start with our metal if we want to. So little steps we've been taking. So how do we balance out? Well, this is a 1. How do I fix it? Put a 2 right there. Yay. So now that I have a 2 right there, 1 times 2 is 2. 2 and 2 is balanced. Okay. Now we have to balance out our oxygens. When we're looking at it, I have a 2 right here and a 3 right there. And you can kind of think this is kind of a trick because oxygen always does this. But when you have a 2 and a 3, what's the common factor between 2 and 3? Well, 6. So if I multiply this by 2, 2 times 3 is going to give me 6. And then if I put a 3 right here, 3 times 2 is, what is that? 6. Yay. That's a common factor. But remember, what did I do here? By putting a 2 in front, I also changed the number of irons. What does that mean? Well, that means I don't have 2 irons over here. I have 4, because 2 times 2 is 4. And so we have 4. Well, I got to balance it out over here. What times 1 will equal 4? Well, just put a 4 right there. And what we see, we can check ourselves. 4 irons, 4 irons. 6 oxygens, 6 oxygens. And now it's our balanced chemical equation. And a lot of times they'll be asked, like, well, what are the coefficients? Well, your coefficients are 4, 3, 2 for this chemical reaction. Let's look at our next one. It says write and balance the chemical equation below. So this one's a little bit harder. Why? Because we actually have to write the chemical equation here. So when we're looking at this, we have copper, which is just Cu, plus silver nitrate. Well, silver is Ag, which always has a +1 oxidation number. Nitrate is a polyatomic ion. It's NO3, -1. And so we crisscross these guys, and we get the equation of AgNO3. Produces silver, which is just Ag, plus copper 2 nitrate. So copper, Cu, it's copper 2, so that means +2. And then nitrate, NO3, with a -1 charge. Crisscross these guys, and we get CuNO3, 2. So we started with a nice balanced chemical equation. Now we just got to go ahead and take this guy or nice written chemical equation, and now we have to balance it. So let's go ahead and move this up so we have a little bit of room to work with. So when we're doing this, we go ahead. What elements do we have? Well, I'm going to treat copper, silver, and then I'm going to treat nitrate as one thing. Why am I going to treat it as one thing? Because I see it on the products and the reactants and it doesn't change. If I saw that the nitrogen and oxygen broke up, well, then I would not treat them as one thing. So when we set it up, now we look at it. What do we have? We have 1 copper on one side. We have 1 copper on the other. We have how many silvers? 1 silver. How many silvers on the other side? 1 silver. On this side, how many nitrates do we have? Well, we have 1 nitrate. And over here we have 2 nitrates. So copper's balanced, silver's balanced. The only thing that's not balanced is nitrate. So guess what? We look at it. What times 1 equals 2? Well, 2. And we see, what does that do? That changes the number of nitrates. Now I have 2 nitrates. But what does it also do? Changes the number of silvers. So now silver is not 1, it's 2. So how do we balance on the other side? Put a 2. You can see that that'll change those 2 as well. And this is our balanced chemical equation. Next one, pretty tough one. It says that Sb4O5Cl2 solid can be produced by reacting solid antimony with antimony 3 oxide with solid antimony 3 chloride. Write and balance the chemical reaction here. So when we're looking at this, we're going to need a little bit of room because it's going to be a tough reaction. So this can be produced from these guys. So we start off, we have Sb, and that's +3, and then oxide is O, -2. And this other one is Sb +3, and chlorine, which is -1. Remember, those are their oxidation numbers. We get the 3 from right there for each of those guys, but this oxygen has -2 because it's in group 16. Chlorine has a -1 because it's in group 17. So we go ahead and from here, and we go ahead and crisscross, and we get Sb2O3 and SbCl3. Now those are reactants, so we go ahead and we write it out. Sb2O3 plus SbCl3 produces our Sb4O5Cl2. So when we're looking at this, we write everything that we're dealing with. O and Cl. We see that we have 2 plus 1, that's 3. And then over here we have 4. Oxygen, we go ahead and look at that. We have just 3 oxygen. On this side we have 5 oxygen. Chlorine, we have 3, and then we have 2. So pretty tough equation for us to balance. When we're looking at this, the first thing we can think of, when we're looking at this, we see our chlorine and it's 3 and 2. Well, just like our oxygen when it's 3 and 2, what's the common factor? When we're looking at this guy, we would think that it's going to be 6. So we could put a 2 right here. And if it's a 2 right there, what has to go here? 3. So we're looking at that. We have our 2 and our 3. Well, that changes a lot of things for us. Yes, it changed our chlorine to a 6 and a 6, but it changes everything else. We have 6 chlorine, but now we have 10 oxygens, and we also have 12 antimonies. And so to balance everything out, now we got to look at, well, what could balance this out? We have on the other side, we no longer have 3, we have 4. And when we're looking at this, we have one guy right here, sorry, 2 right there because of that 2. And so when we're looking at this, what could balance it out? What can balance all of those oxygens out? And that's not 10, but that is, the oxygen should be 15 because 3 times 5 is 15. So we're looking at this, what could balance it out? Well, 5 right here. And let's look. 5 times 2 is 10 plus the 2 that we have sitting over here. That is 12. So yay, 12. And we also see that we have 15 of our oxygens. So really when you're balancing chemical equations, good idea. Make sure we look at it, but it's also keeping up with everything that you're changing and kind of just trying to figure out the puzzle until it works.